Okay, let's tackle 8.2 in Hungerford's undergraduate abstract algebra book, problem 29. Let n be a cyclic normal subgroup of a group G, and H any subgroup of n. Prove that H is a normal subgroup of G. Compare to exercise 14. So, I wish I could let you sort of see the whole process here. It takes some time. In fact, before I wrote this, I was just practicing on scratch paper, and there's some time just sitting still. But here's how I started. I'm going to try to replicate it, but cut out the awkward pauses. So, well, I know that n is a normal subgroup of G, okay, and I know that it's cyclic. So what's cyclic mean? Cyclic means that it's all the powers of A for some A in the group itself. Now, here, remember what I'm thinking there is I'm thinking Gn equals Ng for any G that you choose in the group. So we have a bunch of equivalent things there in theorem 8.17 that we might go ahead and use. But for starters, let's just assume that this is what we have. Let's just start with the definition. I have this. Then I also have that H is a subgroup of n, and I want to show, some people would say need to show, H is a normal subgroup of, now notice there's two things we could say it was a normal subgroup of, n or G. Now since n is a cyclic group, that makes it abelian. Any subgroup of an abelian group is normal, so that's not very interesting. They ask us to show that it's a cyclic subgroup, sorry, a normal subgroup of G. So in essence what we're asked to show is that G capital H equals capital H G, right? That's what we're trying to show. Now, a couple of things. The first thing that should come to your mind is, well, what's special about a subgroup of a cyclic group? So if you'll remember, theorem 717 says that H is in fact cyclic. And it's generated by some, since every element of n is just a power of A, it's generated by some A to the K, okay? For some integer, you could even make it a non-negative integer. Okay, so I know something here. Now, if you think about theorem 811, in fact, I'll show it to you here. We have a tremendous variety. I could show any of these I want to about H to show that it's normal. 3 is sort of my old go-to. Okay, so typically what I would do is I would let G be in G, let some element be in H, so every element here looks like A to the K to the N, right, be in H. We want to show, for normal, that G A to the K to the N, G inverse is in H by theorem 811. This shows H is normal in G. Okay, so you might be thinking about this, and at this point, frankly, I got bogged down. I'm thinking to myself, well, gee, how do I do that? Well, I'm supposed to be borrowing the fact that that property holds for G. So my thinking here, my thought process is something like, I want G A to the K to the N, G inverse in H, well, but and H is the set of things that look like A to the K to some power. So I want G A to the K to the N, G inverse, to equal a to the k to the p. It might not equal a to the k to the n. In fact, it probably won't if it's not an abelian group. But I need it to equal something in H. What do I know? Well, I know that n is normal in G. So I know that G to the a to the any power, right? G inverse equals a to some other unpredictable power. And the problem is, so fine, put in a k to the n. What I'd really like is I'd like to say this is a power of k. And I'm thinking to myself, how on earth can I know that it's a power of k? And so what do? Well, I sit there for a little bit, and sitting there not having a good idea isn't such a great thing. So I start thinking about examples. And obviously, abelian groups aren't very helpful since everything works perfectly in an abelian group. So I think to myself about D4, the dihedral group or the symmetries of a square. And I think to myself, well, in here, what you have is you have the set of, let me say, it's the subset, the zero rotation, the first rotation, the second rotation, the third rotation. However you notate it, you have the rotations. Those are a cyclic group, right? The 90-degree rotation generates all the rotations. That's a cyclic group. And then whatever you're going to call your flip, let's say R1D, and you can check this. So R1D is the same as DR3. Well, that's pretty inconvenient because if you think about these rotations sort of right here, this goes here, and then if you flip, somehow it's as if you had it over there, right? So how does that little game play here? So I'm thinking about this example. I'm struggling with, well, what happens here? I actually looked at exercise 14 like they recommended. Exercise 14 showed that a subgroup of any old normal subgroup is not necessarily normal. They gave an example that wasn't normal in D4, in fact. But then I realized, well, hold on a second. I could move these elements one by one across G and maybe get some effect. So now I'll go back and think about what that looks like. This is what my notes look like. I won't show anybody on this page that I had to work incrementally towards that. I know since n is normal in G, GA equals a to the p G for some p, right? So some people call this weak commutativity, since GA is an element here, right? That means that it must be an element over there, meaning some element, a to the p, is just an arbitrary element of n times g. So this is an element here, so it must be an element there, so it must be something of that form. Well then, what I want to do is I want to sort of look at this guy right here. Well, so what's going to happen as I move elements across? So g to the a to the n k g inverse, okay? I'm going to move one element across, so equals a to the p g a to the nk minus 1 g inverse, right? I've moved one across and I get that, equals a to the 2p g a to the nk minus 2 g inverse equals, I'll just put some dots, equals, well, I'm going to move them all across, so a to the nk to the p g inverse. Ah, well, that's very convenient. G inverse, of course, is the identity, so this equals a to the k to the np, which is an element of H. Therefore, my proof's done. Isn't that sneaky?